Welcome to the All Sorts podcast, where we like to take a deep dive into all sorts of fascinating topics.
That's right.
And today we are diving deep, deep, deep into the world of petrochemicals.
Petrochemicals, the building blocks of our modern world.
It's really incredible when you stop and think about it. I mean, 95%, that's 95% of everything manufactured around us ultimately comes from petrochemicals.
From the clothes we wear to the gadgets we use every day.
To the cars we drive.
To the furniture we sit on.
It's really, really remarkable. And today we're going to be exploring the fascinating world of petrochemicals manufacturing. We've got some great sources. We've got a book called Petrochemicals.
Very concise.
We've also got some really interesting insights from cefic.org. And we are going to use all of that information to kind of pull back the curtain and look at how petrochemicals are made. We'll be exploring the raw materials, the techniques for extracting and processing them, the essential building blocks that emerge, and a really astounding array of products that are created. It's really quite a journey.
It is.
So I guess to kick things off, let's start with the basics. I mean, where do these petrochemicals even come from?
Well, the vast majority of petrochemicals are sourced from petroleum and natural gas.
Okay. Makes sense. But why those two?
Well, a few reasons, really. They're relatively abundant, for one.
Right.
And cost-effective to extract and process.
Right.
Plus, the hydrocarbon molecules in petroleum and natural gas are complex. They can be broken down and restructured into just about any basic chemical we need.
So it's kind of like their nature's Lego set.
In a way, yes.
That's really cool. Now, I've noticed in our sources there's mention of something called refinery gas and process gas. What exactly are those?
Good question. Those are essentially gaseous mixtures that are produced as byproducts. Yeah, byproducts during the refining process of crude oil.
Gotcha.
Their exact composition can vary. It depends on the type of crude oil being refined. But the interesting thing is, sometimes they add lighter hydrocarbons, like propane and butane, back into the crude oil before it's even transported.
Really? Why would they do that?
Well, it's called spiking. And it's done to increase the vapor pressure of the oil, which makes it easier to move through pipelines. But it also means that more of these valuable light components can be extracted later on.
So it's all about efficiency.
Exactly. Getting the most bang for your buck, so to speak.
Gotcha. Now, I've read that the lighter hydrocarbon gases like methane, ethane, propane, and butane are actually the most commonly used in petrochemicals.
That's right. The smaller molecules are incredibly versatile. They're sort of the foundation.
The foundation. Gotcha.
Yeah, for a huge range of downstream chemicals.
Mm-hmm.
But we can't forget about the aromatic hydrocarbon derivatives either.
The what?
The aromatics. Benzene, toluene, and xylene. We often group them together as BTX.
Oh, BTX. Okay.
They're super important as well. Their ring-like molecular structures form the basis for many other crucial chemicals.
Okay, so where do these aromatic compounds come from?
Some are naturally present in crude oil.
Okay.
But most are actually produced from other components within the refinery stream.
Okay. How so?
A process called catalytic reforming.
Catalytic reforming.
It involves using catalysts, which are special materials that can accelerate chemical reactions.
Right.
And those catalysts essentially reshape non-aromatic hydrocarbons into those valuable aromatic ring structures.
So it's a bit like molecular tailoring.
Yeah, a good way to put it.
Very cool. Okay, so we've talked about petroleum, but what about natural gas?
Yes, natural gas, another crucial player.
What's in that?
Well, it's primarily methane, the simplest hydrocarbon.
Okay.
But it also contains natural gas liquids, or NGLs. These are heavier hydrocarbons like ethane, propane, butane, and even larger ones. And you know what? Sometimes they even find those BTX aromatics we talked about earlier.
Really? Right.
Yeah. And of course, there are also non-hydrocarbon gases in there. Things like nitrogen, carbon dioxide, helium, even water vapor.
So natural gas is a bit of a mixed bag.
Exactly. And the specific mix can vary widely from well to well, which naturally affects how it had to be processed to isolate the valuable parts.
Interesting. So we've got these conventional sources. Are there any others? Unconventional ones?
Well, yeah, actually. Some interesting ones, too, like methane hydrates. That's methane trapped in ice crystals under the ocean floor in permafrost.
No way.
Yeah.
That's crazy.
It is, isn't it?
Yeah.
And there's biogas, which is generated from the breakdown of organic matter. Think, like landfills or wastewater treatment plants.
Right.
And then there's shale gas, which has become a big player recently, thanks to fracking.
Right.
Hydraulic fracturing.
So we've got all of these raw materials, conventional and unconventional. What happens next? How do we actually get to the good stuff?
Ah, so that's where the magic
The
happens.
magic.
Yeah. The extraction and processing.
Okay.
For crude oil, a key method is distillation.
Distillation.
Yeah.
Mm.
It's basically you heat up the crude oil and collect the different components as they vaporize at different temperatures.
So it's like a giant tea kettle.
In essence, yes,
Huh.
a very sophisticated tea kettle.
That's a good way to put it.
Then these separated gases are further processed, compressed to reduce their volume. They remove acidic gases like hydrogen sulfide and carbon dioxide, and they dry it to get rid of any water.
Okay.
And then comes the low-temperature fractionation. It's a chilling process that separates the individual gas components.
Wow. That sounds super precise.
It is, and it's crucial to get the right components for downstream processes.
So what happens to these separated gases then?
Well, methane and hydrogen are often isolated through compression and expansion cycles.
Okay.
Methane, it's mostly used as fuel within the refinery itself.
Right.
And hydrogen, after it's purified, becomes a crucial ingredient for hydrogenation reactions. Those are used to upgrade the heavier parts of the crude oil.
Got it.
Now, ethane and propane that are separated,
Yeah.
they're often recycled back into the cracking furnaces for further processing. You get even more ethylene and propylene that way.
Smart. And what about naphtha? That seems to be a big deal, according to our sources.
It is. Naphtha is a vital source of petrochemical feedstocks. It's a mid-boiling range fraction from the crude oil, and it's fed into naphtha crackers. These specialized units convert naphtha, and sometimes heavier gas oil or even LPG, into those essential building blocks: ethylene, propylene, benzene, toluene, and xylenes, among other things.
So naphtha is like the star of the show.
In many ways, yes, it's a very versatile starting point. The process involves pyrolysis or steam cracking, where the naphtha is heated rapidly to extremely high temperatures in the presence of steam.
Sounds intense.
It is. This breaks down the larger molecules in the naphtha into those valuable smaller ones. And then the hot gas mixture is immediately cooled down or quenched to stop further reactions.
And then?
Well, the heavier products can be turned into things like fuel oil, while the lighter gas stream, which is now rich in our building blocks, is sent off to other units for further separation and processing.
Gotcha. So it's a real cascade of reactions and separations, all very carefully choreographed.
Precisely. Now, we also have to talk about gasification, another important technique.
Okay, tell me more about that.
Gasification is used to produce synthesis gas, also known as syngas. It's a mixture of carbon monoxide and hydrogen. They produce it by partially burning carbon-containing materials, things like the residue from crude oil refining, heavy oil, even biomass, in a controlled environment with a limited amount of oxygen.
Okay. And why is synthesis gas so important?
Well, it's super versatile. You can use it to make a lot of things: methane, hydrogen, and even those aliphatic hydrocarbons, which are straight or branched chains of carbon atoms.
And you can control the ratio of hydrogen to carbon monoxide.
Exactly. By changing the amount of steam you use, you can fine-tune the composition of the syngas for different applications.
That's clever. So we've gotten from raw materials to the first stages of processing. Now let's talk about the actual building blocks that are used to make, the everyday products we use.
Right. And our sources say that the big players are methanol, ethylene, propylene, butadiene, benzene, toluene, and xylenes.
Okay, that's a lot to cover. So where do we start?
Well, let's start at the very beginning.
A very good place to start.
Let's start with methane,
Methane. Okay.
that simplest hydrocarbon molecule.
Okay, so what do we get from methane?
A lot, actually.
Like what?
Well, if you react it with sulfur, you get carbon disulfide.
What's that used for?
It's an important ingredient in the production of rayon.
Okay.
And while we primarily produce ethylene through other methods, you can also get it indirectly from methane.
Huh.
And another thing you can get from methane is hydrogen cyanide.
Sounds dangerous.
It can be, but it's a crucial precursor for certain polymers.
Okay, so it's important.
Very much so.
What else?
Well, then there's a family of chloromethane derivatives: methyl chloride, methylene dichloride, chloroform, and carbon tetrachloride.
Wow, that's a mouthful.
Yeah,
And they're all from methane.
you got it. They're typically made by reacting methane with chlorine at high temperatures.
I see.
Oh, and of course we can't forget about synthesis gas, or syngas.
Oh, right, that versatile stuff.
Exactly.
So is that it for methane?
Nope, not even close. There's also urea.
Eureka. What's that?
It's a vital ingredient in fertilizers,
Okay.
and it's made from methane.
Wow, methane really gets around.
It does. And then there's methyl alcohol, better known as methanol.
I've heard of that.
It's another important industrial chemical.
And you make it from methane.
Often by reacting syngas over a catalyst, yeah.
Okay.
And speaking of catalysts, methanol could be further converted into formaldehyde.
Oh, formaldehyde. That's used in all sorts of things, right?
You bet. Resins, building materials, you name it.
So starting with just methane, we can make all of these useful products.
Right. And there's even more we can do with those derivatives. Formaldehyde, for instance, can be used to produce a whole range of other aldehyde compounds.
Okay.
Ethylene glycol, which is common in antifreeze and is essential for making polyester and those plastic bottles we use all the time, can also be indirectly produced from methane via ethylene oxide.
Yeah, I see.
Then you have nitration of methane, although this tends to produce a complex mixture of products. And oxidation of methane can give you a variety of oxygen-containing compounds, including carboxylic acids. And then, if you really want to get fancy, you can alkylate methane or even break it down at high temperatures. That's called thermolysis.
Oh, okay.
These processes can yield things like benzene and ethylene.
Wow, who knew you could do so much with methane?
Right. It's pretty amazing.
Okay, so what about ethane? What kinds of things do we get from that?
Well, ethane is primarily used to produce ethylene.
Okay,
Uh-huh.
so
It's a fairly straightforward process called pyrolysis, or thermal cracking.
cracking.
Yeah. You heat it up to really high temperatures, and the ethane molecule breaks down into ethylene and hydrogen.
That's pretty simple.
Simple but effective.
Right, right. Okay, so we've covered methane and ethane. What's next?
Well, next up is propane.
Propane. Okay,
It's a 3-carbon hydrocarbon.
3 carbons, gotcha.
You find propane used in a lot of different ways.
Okay.
It's a good solvent for certain hydrocarbons,
Yeah.
especially when you're refining lubricating oils.
Okay.
And it's also commonly used as a refrigerant.
Oh, right, like in refrigerators and air conditioners.
Exactly.
And of course, it's a major part of LPG.
Liquefied petroleum gas, yep.
Yeah,
For cooking and heating.
that's right.
Now, chemically speaking, propane is more reactive than ethane or methane
Why is that?
because it has what we call secondary hydrogen atoms in its structure. These hydrogens make it easier for propane to undergo various reactions. It's a good starting point for making olefins, which are hydrocarbons with double bonds.
Okay.
And like methane, propane can also be nitrated. This gives you a mix of nitroparaffins that are used as solvents.
Interesting. So what about butane? That's the 4-carbon one.
You got it. Butane is mainly used for making butadiene and acetic acid.
Butadiene.
Yeah, it's an essential ingredient in synthetic rubber, which is, used in tires and all sorts of other things.
Okay.
And acetic acid is a very common industrial chemical used in everything from vinegar to plastics.
Okay, so butane's got some important uses too. What about butylene? That sounds pretty similar.
It is similar. Butylene actually comes in a few different forms, but it's often oxidized to make acetic acid, maleic anhydride, which is used in resins, and methyl ethyl ketone.
And methyl ethyl ketone is it?
Solvent. Oh, right, another solvent.
Yeah, it's very versatile.
Okay, cool.
Butylene can also be used to make alcohols, and it can be isomerized, which means its structure is rearranged. Okay, or it can undergo metathesis, which is kind of like a molecular swap meet, and oligomerization, which links several butylene molecules together.
Okay, so back to synthesis gas, or syngas. We've already established how we get it from methane and other sources, but what do we actually make from it?
Well, you can make a lot from syngas. For one, it can be used to make more methane through a process called catalytic methanation,
Okay.
or you can use it to make hydrogen.
Pure hydrogen.
Yeah. That's usually done through a process called steam reforming or partial oxidation. And syngas is also essential for something called the Fischer-Tropsch process.
The Fischer-Tropsch process.
It's a really cool chemical reaction. You use catalysts, special materials that help speed up reactions, to convert syngas into a wide variety of hydrocarbons.
Hydrocarbons.
Everything from methane to long-chain waxes.
Wow. And you can even get oxygen-containing compounds like alcohols and organic acids, too.
That's right. The specific products you get depend on the catalyst and reaction conditions.
So it's very flexible. Very. And it's also the starting point for making what we call low, medium, and high BTU gas, which are essentially different grades of fuel gas.
High BTU gas. Is that the same as natural gas?
Pretty much, yeah. It's primarily methane. But since it's made from other sources, we call it synthetic natural gas.
Okay. Makes sense. So let's talk about ethylene. What do we make with it?
Oh, ethylene is the superstar.
Yeah.
It's used in tons of products. One of its main derivatives is ethylene oxide.
Ethylene oxide. Okay.
It's made by carefully oxidizing ethylene over a silver catalyst. And then ethylene oxide is used to make ethylene glycol. That's the stuff in antifreeze. But it's also crucial for making polyester fibers and those plastic bottles we were talking about.
Interesting. So ethylene is indirectly responsible for keeping our engines from freezing and for our plastic bottles.
That's right.
Amazing.
It is. And then if you react ethylene oxide with alcohols or phenols, you get things called alcohol ethoxylates and ethoxysulfates.
What are those?
They're surfactants. You find them in cleaning products, detergents, cosmetics, all sorts of stuff. And we can't forget about acetaldehyde, which is another ethylene derivative made through the Wacker process. And ethylbenzene is produced by reacting ethylene with benzene.
And ethylbenzene is used for
making styrene.
Styrene, I know that's a type of plastic.
You bet. It's used in polystyrene and a bunch of synthetic rubbers.
Yeah.
But the biggest use for ethylene, that would be polyethylene.
Polyethylene, okay.
Yeah. It's made by polymerizing ethylene using those special Ziegler-Natta catalysts. It's the most common plastic in the entire world.
That's incredible. So much comes from ethylene. So what about propylene?
Propylene's another big one. You can oxidize it to make propylene oxide. That's a key ingredient for polyurethanes.
Okay.
You can also react it with sulfuric acid to make isopropyl alcohol.
Isopropyl alcohol. That's rubbing alcohol, right?
Right. And that can be further processed to make acetone.
Acetone, that's another solvent, right?
Exactly. A very common one.
Okay. Anything else we get from propylene?
Absolutely. Acrylic acid, that's another one, made by oxidizing aquilene. You can even make allyl alcohol and glycerol from propylene.
Glycerol, I know that's in soap.
It's used in all sorts of things, pharmaceuticals, cosmetics, you name it.
Wow, so propylene is just as versatile as ethylene.
It's right up there. It's also the base for making polypropylene, which is another major type of plastic.
Oh, right. Polypropylene, what's that used for?
Oh, tons of things. Packaging, car parts, textiles, it's everywhere.
I see. And again, it's made with those Ziegler-Natta catalysts.
That's right.
Wow. So we've got ethylene and propylene covered. What about butadiene?
Butadiene. Mostly used to make polybutadiene.
That's a type of rubber, right?
It is. A synthetic rubber known for its durability and elasticity. You make it through a process called emulsion or anionic polymerization.
Okay. Anything else from butadiene?
Oh, yeah. It's also used to make adiponitrile.
Adiponitrile, okay.
And that, in turn, is processed further to make adipic acid and hexamethylenediamine.
Now, they're
the two building blocks for nylon 66.
Right. Nylon.
Exactly. A very important and strong synthetic fiber.
I see. So butadiene's pretty important, too.
It is. You also make chloroprene from butadiene.
Chloroprene, what's that?
That's the monomer for neoprene rubber. It's great because it resists oil and weathering.
Oh, right. Neoprene, like wetsuits and stuff.
Yeah.
Cool. Okay, so what about acetylene? That's the one with the triple bond, right?
Yep, that's the one. Acetylene production isn't as big as it used to be, but it's still important.
What do we make from it?
Well, one of its big uses is making acrylic acid and its esters. They're often used in paints and adhesives.
I see.
You can also use acetylene to make vinyl chloride, which is used to make PVC and acetaldehyde. Although these days it's more common to make acetaldehyde from ethylene because it's cheaper.
Oh, right. We talked about that earlier.
Yeah. One problem with acetylene is that it's tricky to ship safely in large quantities.
Why is that?
It's very reactive, so it tends to be consumed close to where it's produced.
Okay. So last but not least, we have those aromatics, benzene, toluene, and xylenes. They seem to be everywhere.
They are.
So let's start with benzene. What's it used for?
Well, one major use is in the production of ethylbenzene, which, like we already discussed, goes on to make styrene.
Right, styrene.
Yeah. Benzene is also used to make cumene.
Cumene?
Yeah, and that's then converted into phenol and acetone through the cumene process.
Right.
Another use for benzene is to make cyclohexane,
That's used for.
making nylon 6 and adipic acid.
Okay.
And then there's linear alkyl benzene, which is a key ingredient in biodegradable detergents. And finally, benzene is also used to make aniline.
Aniline.
It's used in dyes and pharmaceuticals.
Okay. So benzene is definitely a busy molecule. What about toluene?
Toluene is widely used as a solvent in various industrial applications. It's also a common ingredient in gasoline. It helps improve the octane rating.
Okay.
But you can also dealkylate toluene to produce more benzene.
So it's a source of benzene as well.
That's right. And fun fact, toluene is also a precursor to benzocaine. You know, the stuff that numbs your mouth.
Oh, right.
You find it in Cepacol and things like that.
Okay. Cool. So what about xylenes?
Xylene actually comes in 3 different forms, or isomers.
Okay.
And those isomers can be separated and then isomerized, meaning they're rearranged to get the desired form. That's often done using catalysts.
Okay. And once you've got the right isomer, what then?
Then they're mostly oxidized to make phthalic anhydride and terephthalic acid,
Phthalic anhydride, terephthalic acid, those are...
essential building blocks for polyesters. You know, the stuff used in fabrics and plastic bottles.
I see. So xylenes are pretty important too then.
They are.
Okay, we've talked about all sorts of interesting compounds and chemical processes. What about polymers and plastics? They're kind of like the poster children for petrochemicals, right?
They are. And it's fascinating to realize that pretty much all addition polymers, the ones made by joining lots of small molecules together, come from olefins, the hydrocarbons with double bonds that we've been discussing.
Right.
These polymers are formed through polymerization reactions where tons of small molecules, called monomers, link up to form long chains.
And how does that linking actually happen?
Well, there are a few different ways. There's radical polymerization, K-Scheenack polymerization, and anionic polymerization.
So many types.
And each of these is initiated by a different kind of reactive chemical species.
I see. Are there any special catalysts involved?
Oh, yeah. The Ziegler-Natta catalysts are particularly important.
Okay.
They're what allow us to polymerize those alpha olefins, like ethylene and propylene, to get the polyethylene and polypropylene we use every day.
Okay. And our sources also talk about thermoplastics and thermosets. What's the difference?
Ah, that's a good point. Thermoplastics are polymers that could be softened by heat and then molded into different shapes.
Yeah.
And you can do that over and over again without changing the chemical structure much. Think about things like polyethylene, polypropylene, PVC, polystyrene.
Okay, gotcha. And thermosets?
Thermosets are different. They change chemically when you heat them up the first time. They form really strong cross-links between the polymer chains, which makes them rigid.
Mm-hmm.
And, they can't be softened again. Think Bakelite or those polyurethane foams.
So once a thermoset, always a thermoset.
Exactly.
So can you give us a few more examples of these polymers and what they're used for?
Sure. We already mentioned polyethylene and polypropylene.
The superstars.
They're incredibly versatile.
What are they used for?
Packaging, containers, films, fibers, you name it.
Okay. What about PVC?
Polyvinyl chloride, that's another big one. It's super durable, so it's used a lot in pipes, window frames, and construction materials.
Okay, I see. And polystyrene?
That's the stuff in styrofoam.
Oh, right.
It's also used in packaging and things like appliance housings.
Okay. What about nylon?
Nylon is a type of polyamide.
Polyam.
Yeah. They're known for their strength and resistance to wear and tear.
Okay. And there are different types of nylon, right?
You bet. There's nylon 66, which we already talked about, made from adipic acid and hexamethylenidyamine. It's used in textiles and a lot of industrial applications. And there's nylon 6, which is made from a molecule called caprolactam. And then you have nylon 11 and nylon 12.
Wow, so many nylons.
They each have slightly different properties depending on what they're made from.
Okay, so what about polyesters?
Polyesters are often made from ethylene glycol and terephthalic acid.
And those are used...
Fabrics and plastic bottles mainly.
I see. Anything else? Any other big polymers?
Oh yeah, loads. Polycarbonates are used a lot because they're impact resistant. Polyether sulfones are good for high temperature applications. Polyphenylene oxide is used in electrical parts. Polyacetal is known for being stiff and slippery, so it's used in gears and things.
Yep.
And then there are all those butadiene-based polymers and copolymers we talked about, like polybutadiene and styrene-butadiene rubber. They're the ones that give tires their elasticity and bounce.
So it seems like polymers and plastics are everywhere.
They are. You find them in just about every product imaginable.
It's amazing how so many different materials can be made from just a few simple building blocks.
It is. It's a testament to the creativity and ingenuity of chemists and engineers.
It really is. Now, our sources indicate that petrochemicals are used in a lot more than just fuels and plastics, right?
Absolutely. They're used in all sorts of things.
Like what?
Well, for example, they're crucial in the pharmaceutical industry.
Pharmaceuticals? What do you mean?
A lot of the active ingredients in medicines,
Yeah.
the stuff that actually makes them work, come from petrochemicals.
Really? I had no idea.
It's true. And not just the active ingredients, but also things like preservatives, flavorings, and colorings.
So even the inactive stuff comes from petrochemicals.
Often, yeah. In fact, our sources list benzene, methanol, phenol, toluene, and xylenes as some of the key starting materials.
Wow.
Even common drugs like aspirin and benzocaine are made using these building blocks.
I see. So what about other industries?
Well, there's the dye industry. Many of the dyes we use for textiles, inks, and paints are derived from petrochemicals.
Huh. And I assume they're used as solvents, too.
Of course. Solvents are used all over the place in all sorts of different industries, and many of them are petrochemical based.
So are there any other surprising applications for petrochemicals?
Absolutely. Take agrochemicals, for example. Things like insecticides, herbicides, and fertilizers often rely on precursors that come from petrochemicals.
Okay.
Then there's carbon black, the stuff that makes tires, inks, and paints black.
Right.
That's made from natural gas or from the heavier aromatic-rich residues left over from refining petroleum.
Wow. I really didn't realize how widespread the use of petrochemicals is.
It's truly remarkable. And we can't forget about the essential inorganic chemicals that are also produced from these sources.
Inorganic chemicals.
Right. Like sulfur and sulfuric acid, both incredibly important in many industries. They're often recovered from sour gas.
Sour gas.
It's natural gas that contains hydrogen sulfide and carbon dioxide.
Gotcha.
And then there are things like ammonia and nitric acid, which are essential for making fertilizers and explosives. They're produced from hydrogen and nitrogen, which are often obtained from refineries.
Wow.
There's hydrazine, which is used in everything from pharmaceuticals to rocket fuel.
And what about carbon dioxide and carbon monoxide? They're just waste products, right?
Not necessarily. They can also be quite useful as chemical feedstocks.
Wow. So petrochemicals are truly everywhere?